Hello, class, and welcome to Chapter 4 in our environmental biology class. It's great to have you guys here for this lesson where we talk about different ecosystems and how they relate to the physical environment. So we'll talk a little bit about how materials cycle through these ecosystems. We'll talk about solar radiation, weather, climate, the global ocean, the atmosphere, and other internal planetary processes. As we look at kind of an introduction here, let's talk about the Hubbard Brook Experimental Forest. This was an experimental area in the White Mountains in the 1950s, serving as kind of a collection for long-term ecological data, especially on the data of salamanders and the effects of deforestation. What they did is they measured the chemistry of the stream water after the forest was logged and cut down and deforested, and compared to the control catchment where an area was unlogged. Let's talk about how materials then cycle through these ecosystems. Matter always moves among organisms, ecosystems, and the abiotic environment. This is the non-living environment. And biogeochemical cycling describes these interactions between biological, geological, and chemical aspects of the environment. We have 5 major cycles that we'll talk about: the carbon, nitrogen, phosphorus, sulfur, and water or hydrologic cycle. The carbon cycle describes the transfer of carbon throughout these ecosystems. Carbon in the air is in the form of carbon dioxide. Plants use it through photosynthesis. We have chemical combustion of plants. Carbon will be released from waste material and animals. We see carbon in coal, the soil, natural gas, fossil fuels. So you can see how carbon dioxide is cycled, used in plant and animal respiration, given off into the atmosphere, and then picked up again by photosynthesis. So we have this cycling of carbon called the carbon cycle. Much of carbon is also dissolved in water, given off as erosions or combustion due to human and other natural uses. The global circulation of carbon between living and non-living environment is called the carbon cycle, and the major processes involved in the carbon cycle are photosynthesis, respiration, mainly in the soil, combustion of fossil fuels, and carbon dioxide dissolving into the ocean. The carbon silicate cycle shows how over many years carbon will interact with the silicate cycle, and this is when carbon dioxide with rainwater becomes H2CO3 and will slowly weather the silicate in rich rocks. Calcium minerals will be released in this process, and then ocean organisms will use the calcium and silicate to form shells. When they die, the shells become buried and over time form into limestone, and geological uplift or subduction can be seen to look at this limestone. Human effects on the carbon cycle. So carbon dioxide, you can see in the 1700s, was about 0.29% of the atmosphere. In 2014, it slowly rose, and it's expected to continue to increase from 0.04% to 0.06% by 2100. And the higher carbon dioxide can potentially create lots of feedbacks in the environment, where we'll have greater carbon dioxide dissolved into the ocean. Then we get into the nitrogen cycle. So there's actually nitrogen is a diatomic element formed as N2. It's actually the most common gas in the atmosphere. So we have a lot of nitrogen that is picked up through biological, what we call nitrogen fixation, where bacteria pick it up. Nitrogen is found in the root nodules and soil. We have nitrogen fixation from human activity, and then it will decompose. And we can see how through ammonium and ammonia, it will kind of cycle through the soil in this nitrification, usually in bacteria. Then it will become assimilated into plants and animal proteins and brought back up into the atmosphere. So we have the nitrogen cycle. Nitrogen is really important because it's needed for proteins and nucleic acids, which makes up the DNA of all living organisms. The atmosphere, like I said, is mostly nitrogen, but most cannot be used in this form. So there's 5 steps in the nitrogen cycle. We have nitrogen fixation, nitrification, assimilation, ammonification, and then denitrification. The Nitrogen cycle, we're going to show kind of in these 5 steps. We're going to break it down here. And you can see how different chemical compounds involving nitrogen will kind of go through this cycle as it continues to be broken down. We first have nitrogen in the atmosphere, which is the most common form, but it cannot be used. So nitrogen is fixated into Na3 or Na4. Those are the ammonia and ammoniums. Then through nitrification, it will be broken down into NO2 and NO3. It will become assimilated into plants, where plants will use that nitrogen kind of elemental base. And then through more assimilation and ammonification, and then denitrification, it will become its original form as nitrogen. So that's a look at the nitrogen cycle and how it cycles through the ecosystems. This kind of gives you a little more information about what all those words mean. Nitrogen fixation occurs by bacteria in lightning, volcanoes, or other industrial processes. Nitrification is when soil bacteria convert NO2 to NO3. Assimilation is when plants absorb these compounds of NO3, NH3, and NH4. And then because when plants absorb it, it will move into the food web or food chain as different animals and primary composers will eat those plants. Ammonification is when bacteria convert that organic nitrogen into NH3 or NH4. And then denitrification is when bacteria will convert the NO3 back into nitrogen, the diatomic element, and we start the nitrogen cycle all over again. An end to that diatomic element is mostly found in just the atmosphere as a gas. Human effect on the nitrogen cycle. Humans have almost doubled nitrogen fixation through fertilization production, which is great for efficiently growing vegetables, but nitrogen pollution in natural environments can cause eutrophication, which is the over-fertilization of forests. And also the combustion of fossil fuels will produce the photochemical smog, and this increases the production of acid rain, which has nitrogen in it. Then we move on to the phosphorus cycle. So you can kind of see how phosphorus is cycled through rocks, through animals, through mining, fertilization, animals and crops, how you can see how it will be in the soil through erosion and dissolved in the oceans. So phosphorus cycles from the land to the ocean sediments and then back to the land. There's not a gas phase to phosphorus, but dust storms can blow phosphorus forms into the atmosphere. When we weather phosphorus-rich rocks into the soil, that can change them into PO4, and plants will observe phosphorus, for example, using it as adenosine triphosphate, and eventually it's carried to the ocean and then sedimented in layers. Human effect on phosphorus, the big one is phosphorus fertilizers. One of the primary limiting nutrients for plant growth are these phosphorus fertilizers. Wastewater treatment plants do not remove phosphorus, and this can also cause eutrophication. And examples that we talked about in Lake Washington in that chapter 1 example. In 2014, there were 7 commercial wastewater treatment plants recycling phosphorus and other nutrients from treated sewage. And there are business opportunities which are abound in the environmental fields to try to figure out how to get phosphorus out of wastewater treatment plants. And then the sulfur cycle, again, starting from kind of a hydrogen sulfide plus oxygen, we get sulfur oxides into sulfuric acid, which then will be decomposed in the ground, circulating through different plants and animals into the ocean and then back into the soil. The sulfur cycle is probably our least understood cycle. Sulfur is found primarily in the sedimentary rock, which can weather and erode. It can come from sea spray, dust storms, volcanic cycles. The main biotic cyclers of the sulfur cycle are bacteria found in the ocean, salt marsh, which gives it kind of a rotten egg smell. I'm sure you've smelled that sulfur smell before, as well as in fossil fuels. Sulfur can contribute to greenhouse gases. And then we get to the water cycle, which is probably the easiest to understand and one you learned about since grade school days, is the water cycle. And we'll talk about how it moves through the atmosphere and up and down. So the water cycle cycles among organisms, atmosphere, land, and oceans. All organisms use water. Transpiration is the loss of water vapor from land plants, and 97% of plant water can be lost this way. This is super important in deserts when we're talking about desert plants. Human effects on the water cycle. So air pollution may decrease precipitation. It may decrease precipitation. There's pumping, diverting surface and groundwater for irrigation. And then potentially in climate change, the warming temperatures could melt the polar ice caps, causing the sea level to rise, causing a potential greater frequency of storms. Solar radiation. So the sun provides energy for all life. It powers the biogeochemical cycles and determines the climate. Albedo is the reflectance of the solar energy off the Earth's surface. If we see dark colors, this signifies a low albedo, where the forests and oceans will absorb some of that sunlight. And the lighter colors mean there's a higher albedo in, for example, in the ice caps, which will reflect that solar radiation. Temperature changes with latitude. So the solar energy does not hit the Earth uniformly, and that's due to the Earth's spherical shape and tilt. So for example, right on the equator, there's a higher concentration of these light rays coming directly straight down, kind of like how this flashlight is shining down on that unit surface area. So that means there will be a greater temperature and little reflection on those parts of the world. As we get closer to the poles, the light rays hit the Earth at an angle due to the tilt of the Earth. So closer to the poles, we get a lower concentration of these light rays hitting the Earth, a higher reflection of those sun rays, and just a much lower temperature at the poles, which makes sense. It's very cold at the North and the South Pole. The seasons. So temperature changes with the seasons. The seasons are determined by the Earth's tilt. So the Earth tilt is at about 23.5 degrees. So you can see here, I'm just going to draw an axis through the globe, through the North and the South Pole. And you can see how it's tilted at about 23.5 degrees. Then as the Earth travels around the sun, different sides of the globe receive more of the sun's light rays during different seasons. So for example, in the summer, the sun's light rays are much stronger on the northern hemisphere. So that's why in the summer, the northern hemisphere will go through summer. As we go through winter, you can see how the sun rays will actually be stronger on the southern hemisphere. So that's why in places like Chile and South America, they will experience those summer temperatures in the winter months. The atmosphere. So the content of the atmosphere I mentioned before is mostly nitrogen, next oxygen, and about 1% of other gases. There are greenhouse gases that make up the atmosphere as well. And the density of the atmosphere decreases with distance from the Earth. And the atmosphere is really important for shielding the Earth from high energy radiation. As we look at the atmospheric levels, this is really interesting to note. The troposphere is where weather occurs. So this is what we're in, the 0 to 12 kilometer range. This is where weather occurs. Temperature will decrease with altitude. The stratosphere is the 12 to 50 kilometer range, where temperature actually increases with altitude and it becomes a very stable layer. The ozone layer absorbs UV light rays, and this is where jets fly. And then the mesosphere, we have the 50 to 80 kilometer range. This is when temperature again starts to decrease with altitude. The thermosphere is the 80 to 480 kilometer range. This is when gases are very thin in the air. They will absorb X-rays and shortwave UV radiation, which makes it very hot. This is the source of the aurora borealis, and they reflect radio waves with the need for satellites in this area. And then the exosphere is the outermost layer. This is when the atmosphere continues to thin until it converges with interplanetary space. Atmospheric circulation. So near the equator, warm air rises, cools, and then splits to flow toward the poles, the North and the South Pole. So you can see how the trade winds bring winds to the equator. So I'm just going to point the trade winds bring winds to the equator, where it will rise, and then those winds will go to the poles. At about 30 north and 30 south latitude, You can see here the air sinks back to the surface, and then air moves along the surface back towards the equator. So it rises, cools, and then comes back to the equator. This also occurs at higher latitudes as well, where it moves heat from the equator to the poles. Surface winds. So these are large winds due in part to pressures caused by the global circulation of air. And the left side of the diagram shows these surface winds kind of circulating hot and cold air. Wind always will blow from a high to low pressure, as you can see on the right side of the diagram. The Coriolis effect describes how Earth's rotation influences the direction of wind. So Earth always rotates from east to west, and this deflects wind from the straight-lined path. The Coriolis effect, due to the Earth's tilt, influences the Earth's rotation on the movement of air and fluids. So it turns them right in the northern hemisphere and turns them left in the southern hemisphere. So here we have, for example, a rocket being launched from the North Pole towards New York along the 74 west longitudinal line. Notice the direction of the Earth's rotation. And as the rocket travels to New York, the Earth's rotation actually causes the rocket to head west of its intended path, shown in that red line. Similarly, a rocket launched from the South Pole towards New York would head west of its intended flight path. Because of the rotation of the Earth, it will move slightly off path. Patterns of ocean circulation. So prevailing winds actually produce ocean currents and generate gyres. For example, the North Atlantic Ocean, trade winds blow west, westerlies blow east, and this creates a clockwise gyre in the North Atlantic Ocean. And the circular pattern is also influenced by the Coriolis effect. So this is really interesting to see patterns of ocean circulation due to trade winds and westerlies. We actually have water circulating in the oceans shown by these patterns. And this is important to know because this will bring the warm water to colder regions and cold water to warmer regions. Position of land masses. So the large land masses in the northern hemisphere help to dictate ocean currents and flow. And there's very little land in the southern hemisphere, so Antarctica is very small. And the land masses in the southern hemisphere, as you can see on the right side of this picture, are much smaller compared to the land masses in the northern hemisphere. We have vertical mixing of oceans where ocean water varies in density. The Gulf Stream and the North Atlantic Drift deliver heat from the tropics to Europe. Heat transferred is then transferred to the atmosphere. It becomes denser, it sinks, and then there's about 8 degrees Celsius cooler than the surface current. The ocean conveyor belt affects regional and possibly global climate. It has shifted about 11 to 12 kilohectares, and the climate change could result in a mini ice age, potentially, some say. Ocean interaction with atmosphere, El Niño Southern Oscillation. This is the periodic large-scale warming of the surface waters of the tropical Pacific Ocean. It happens every 2 to 7 years, and it prevents the upwelling, pictured on the right, of nutrient-rich waters off of South America. So in normal conditions, the westward blowing trade winds keep the warmest water in the Western Pacific. So for example, we have an accumulation of warm water. Warm, moist air rises, causing low pressure and heavy rainfall. Cool, dry air will then descend with high pressure and little rainfall. And then the upwelling of the nutrient-rich water, called the Humboldt Current, will occur just off of South America. So really interesting to see how these winds affect ocean currents and then potentially weather. More about El Niño conditions. Trade winds will weaken and warm the water as it expands eastward to South America. And this actually has a big effect on the fishing industry off South America, causing floods in Peru. Australia and Indonesia will have droughts. And La Nina is when water in the East Pacific cools and west trade winds will strengthen. Weather are the conditions in the atmosphere at any given place and time. It includes the temperature, precipitation, cloudiness, etc. So that's weather. Climate is the average weather conditions that occur in a place over a period of years. And there are two most important factors to climate: temperature and precipitation. Here are the climate zones that you can see here: world climate in general. When we talk about human equatorial climate, dry climate, humid temperate, cold, and highland climate. And we'll go over some of these now, but you can see how the regions really kind of start at the equator and then are cooler as you move away from it. Rain shadow. So mountains force humid air to rise. As air cools with altitude, clouds form and precipitation occurs on that windward side of the mountains. But because those clouds lose all their precipitation, that dry air mass then moves to the leeward side of the mountain and we get a rain shadow. This is what's happening in areas like Las Vegas and, parts of Arizona, that, all of these moist air clouds lose all their moisture on the windward side of the mountains. And then as that air mass moves over several mountain ranges, by the time it gets to the leeward side of those mountain ranges in Las Vegas and parts of Arizona, you really get into a rain shadow desert, and that's why it's very dry. The True Colors satellite image of Oregon shows this rain shadow effect. This is such a cool picture, a satellite image showing the green windward side of the mountain ranges, dropping all the precipitate, and how on the eastern side of Oregon, we see a much drier leeward side when that air mass just does not have as much precipitate to drop. I grew up in a little town in eastern Oregon near Bend, and it was very dry. It was a beautiful climate, but very dry. Tornadoes are powerful funnels of air associated usually with a severe thunderstorm. They form when you have a strong updraft of spinning air, forming as mass of cool, dry air collides with warm, humid air. The spinning funnel becomes a tornado when it descends from the cloud, and it can have a wind velocity up to 300 miles per hour and a width as large as 2 miles. And the United States has more tornadoes than anywhere else in the world. Tropical cyclones are giant rotating tropical storms where the wind can be, from 73 miles per hour as much as 155 miles per hour. And these form when strong winds pick up moisture over the warm surface waters and then start to spin. Due to Earth's rotation, the spin causes an upward cycle of clouds. Tropical cyclones can have many names. They're called hurricanes if they're in the Atlantic, typhoons if they're in the Pacific, or cyclones if they're in the Indian Ocean. So here we have a look at some of these tropical storms, showing how warm air rises, they start to spin, really leading to some dangerous weather. Tropical cyclones, the frequency of hurricanes varies annually. 2005 had the most active record with Hurricane Katrina. Other factors that influence the formation include precipitation in Africa, water temperatures in the Eastern Pacific, the wetty rain season and the Sahel Desert in Africa, as you can see there, and dissipation of the El Nino effect. Hurricane Katrina was the hurricane off the north central Gulf Coast in August of 2005. The storm surge severely damaged New Orleans and flooded about 80% of the city. The eroded Mississippi River Delta region contributed to that damage. And with the area's development, engineers built canals and levees. The river normally resupplies sediment building up that delta, but New Orleans is sinking. It has no bedrock, which lends itself to a potentially dangerous situation in the future. Internal planetary processes. So the layers of the Earth are shown here. The lithosphere is the outermost rigid rock layer composed of the plates. The asthenosphere is the lower mantle comprised of hot, soft rock. Plate tectonics is the study of the processes by which the lithosphere plates move over the asthenosphere. And the plate boundary is where two plates meet. We can have a divergent plate boundary when two plates will move apart from each other, a convergent plate boundary when two plates collide with each other, and then transforming means when the plates move horizontally, opposite but in parallel to other plates. So here's a look at plates and plate boundaries, and normally you have more earthquakes at these plate boundaries where plates have come together. So you see the San Andreas Fault, probably the most well-known for us in Southern California, but you can see how all over the world there's different plate boundaries. And again, at these plate boundaries, you can see if they're divergent, convergent, or transforming. So you'll see a lot of these plate boundaries will be where you have a lot of earthquakes. Earthquakes are caused by the release of accumulated energy as rocks in the lithosphere suddenly shift or break. They will occur along faults, and energy is released as a seismic wave, which we can study. The Richter scale measures the magnitude, and each unit is 30 times larger. We cannot feel magnitude 2, and landslides and tsunamis are usually side effects of earthquakes. A tsunami is a great undersea wave caused by an earthquake, a volcanic eruption, or a landslide. They can travel upwards to 450 miles per hour, and tsunami waves may be only 1 meter deep in the ocean, but they can become as much as 30 meters high on the shore. For an example, we had a 9.3 magnitude earthquake in the Indian Ocean, and this triggered a tsunami that killed over 230,000 people in South Asia and Africa. Volcanoes are when magma pushes through the plate, reaching the surface, becoming lava. Volcanoes occur at subduction zones, spreading plate zones, or above hot spots, where you have a rising plume of magma that flows from the rocky mantle to the opening in the crust. The Ring of Fire in the Pacific Basin is where we have a lot of volcanoes. Mount Pinatubo in 1991 spread out an ash cloud up to 30 miles upward. So here we have examples of volcanoes releasing lava or just a lot of ash. Hawaii is the youngest major island and the only one with active volcanoes, but you can see some of those other volcanoes in the Pacific Plate. Enviro news, so we always end each chapter with a little bit of news. And again, our textbook is, well, it's not super old, but so some of this is relatively recent. 2 coastal Sri Lankan villages, one with extensive mangroves and the other completely deforested, often to build tourist resorts or for aquaculture. The village with the intact mangrove forest recorded only 3 deaths in this tsunami, and the village which was cut down all its mangroves had about 6,000 deaths because without the mangroves, it wasn't able to kind of hold the soil in place. And due to that tsunami, the soil eroded away, causing much more flooding and dangerous conditions. The mangroves can help buffer those storm surges. So thank you for listening to chapter 4, and we'll see you for chapter 5.